Hi, everybody. So, welcome to the group meeting of Statistical Physics Group in the Department of Physics, Universidad de Guadalajara. So, here basically each and every week we meet, and each week there is a talk going on for this group seminar. And from today, we will put this group seminar as a live streaming in YouTube. So as you can see that we are this specific seminar for this semester have started 3 weeks back. There are 3 seminars already happened. One is already in the YouTube, one video. There will be 2 more coming. So, and today it will be the live streaming. The talk will be in English, and the talk will be presented by José Luis Parra, who is an undergraduate student doing his thesis on undergraduate student in Spanish, estudiante de licenciatura. He will present his talk today. The title of the talk is the Introductory Seminars, Introduction to Network Theory. He is doing his thesis with Dr. Thomas Gorin on random Hopfield network. So, Jose, the platform is yours.
Thank you very much for introducing me, Dr. Soham, and thank you for joining us for everyone. As Soham said, the topic is Introduction to Network Theory. Here is our overview, some basic concept in the graph theory, which is the base of the network theory, something interesting measurements in the network that we can make in the empirical, in real network. I want to show you an empirical result for the study in internet. And finally, I'm going to present you some models to study how a real network grows up or are connected. Okay, where first, a network is a collection of connected objects. Each object will be a node, and the connection between two objects is given by the age. The first challenge is to make real phenomena in the nature looks like a network. So let me give you some example of this. Here, for example, we have how the internet looked some years ago, how internet web pages are connected between them. Another example, here we have a picture of how some users are connected between them in Twitter in the political global context. Some interesting thing in this picture is the fact that we have cluster. We are going to discuss what is a cluster. Each account is a node, and we have a relation. And we are going to study the cluster. And one interesting thing, for example, is how many counts are clustered between them. For example, the green ones are related to Latin America, and the purple one to Europe. Here in Twitter, each user is a node, and if two users follow the other one, then there is an age between them. Here, for example, we have Donald Trump and the royal family account, and the followers and followings are how many users they are related. Okay, now a biological example. In this picture, we have a brain, an adult brain representation. Different areas of the brain are represented by the red dots, and the links between them are the blue lines. Another example here, what about a network that represents the metabolic process? Here, the interesting thing in this network is that the network not only just shows us the connection between the nodes, it also shows in which direction some metabolic process goes, and how many of the reaction correspond to a specific process. And my favorite example, a worm. In the Open World project, they are working to simulate one simple living being. In this case, the worm. They are representing They represent how different organs are connected between them. And this is actually an open source project, and anyone can check their job. So as we can see, the fact is that there is a lot of phenomena that can be studied as a network. As I told you in the first challenge, is make that phenomena looks like a network. Before, we are going to study the properties of the network that we create. We are going to start by present you these three peoples. The first one, Leonard Euler, by solving the Kingsberg bridge problem, he developed a new area in mathematics that is the random graph. In the last century, Paul Erdos and Alfred Rennie bring the idea that some graphs in nature are connected randomly. The idea is that two nodes are connected by a probability rules, and these have give how we understand the study in network nowadays. Let's go to review some basic concept. The first one, a graph. A graph is defined as a set of P of n nodes. EH, A is the edge of the is the set of edges that connect those elements. Another important concept is the node degree. K, the node degree K is the number of edges of the node P, A, where they are connected. For example, in the picture we have here, we have a graph with 5 nodes and 4 edges. There is a node, the node 1, for example, has a degree 2, and the node 5 has a degree 1. In other hands, the node 4 has no degree. Another important concept is the distance between two nodes. This is defined as the shortest path connection between two nodes. There are also here in the picture, we can see a connection between the node 1 to 3 by a direct edge. In this case, we have a distance 1. But if we go to 3 by the way of the node 2, we have a distance. We have a distance 2. Obviously, the first one is the best selection for the distance between these two nodes. However, the definition could be arbitrary, and for another purpose, we can define another definition. Another interesting basic concept is the definition of a subgraph. If I can make a graph with the elements of a bigger one, this will be a subgraph of the bigger graph. The formal definition tells us that the graph G1 is a subgraph of G if all the nodes P1 are also nodes of P, and all the edges of E1 are also edges of E. The other definition is the cycle. The cycle of order key will be the loop of the edge, such as two consecutive edges has a common node. Here, for example, I can write the node 1, 2, and 3 as a subgraph, and 4 could be also a subgraph. And 1, 2, and 3 is actually a cycle defined by this definition. Okay. Now, the connection in a graph can be represented as a matrix. This will be named the adjacency matrix. This is a square matrix that represents how the node A and J are connected. If the adjacency matrix is symmetric, we must say the connection will be bidirectional. In other hand, if there is no a bidirectional connection, the entries of the matrix will be not the same for the entry AG and GA. We can imagine, for example, that we are in a car. If we took a street by two ways, that will be a bidirectional connection. But if the street has only one way, that represents an unidirectional connection. Okay, another important thing is that usually the connection is represented by 1 and 0 otherwise. However, these entries can be represent the strength connection between nodes of the elements. My best example is a neural network where each neuron could have a different connection between them. Okay, here we have our symmetric metrics for the same graph that I have used. And given that we are working with metrics, we can study the properties of these metrics. And as we know, one of the important things in a matrix is the eigenvalue of this matrix. If we have a graph on net nodes, we have n eigenvalues for each adjacency matrix. And given that we have a matrix, the eigenvalues give us an important information about the topology of the network. And this is useful to define the spectral definition given by the equation 1. The spectral density can be directly linked with the network topology features. And for a random graph, the spectral density follows a semicircle distribution. This semicircle distribution has a lot of application in quantum, statistical, and other areas in physics. Here we have how a semicircle distribution looks like. And we can see for network theory, another important tools is the random matrix theory and the probability theory. Okay, in real network, now we are interested in the study of real network. In the real network, not the nodes has the same degree. Remind that the node degree is the number of edge that a node has. Okay, for the most of the random graph, the degree distribution follows a Poisson distribution with a peak in the average of the node degree. In real network, this distribution divides from the Poisson distribution, and for large network, the distribution have a power law tail. Here, for example, we have the Poisson how a Poisson distribution looks like. And the important thing when we are talking about the decay in the power law tail is how we get this behavior in the Poisson distribution. The distribution, okay. Fine. Okay, another important concept will be the clustering coefficient. This measures the tendency at which some nodes tend to cluster together, be related between them. For the node A, the clustering coefficient is given by the equation 3, where AE is the age of the node E, and the KE is the node degree of the node. For the equation 4, we have the clustering coefficient for the whole network, where we took the average of the clustering coefficient for each node. Okay. Okay. And finally, the small world concept. This describes the fact that for a large network, there is a relative path that connects two nodes. There is a relative short path that connects the node. This is not a particular organizing principle, but okay. Thomas Goring has a question.
Yes, it's sorry for the to the previous slide. I think I did not get what the in the nominator you have EI, right?
Yes.
So that is what?
This is the age of the node E. How many age that the node are related in them?
It's not the number of nodes in the environment or so? Because K sub I is the number of edges, right?
Yeah, yes. You are right. Thank you.
Okay.
Sorry, thank you, Dr. Goring. Fine. Okay. Well, the small, as I told you, the small world concept is not an indication of particular organizing principle in the network. However, this is interesting how some networks present this phenomenon. The most important or the most popular example was given by Stanley Milgram. This psychologist said that in United States, each citizen is a node, and this node has an age with every person that it's node. Milgram said that the distance between two nodes, between two different citizens in United States, is equal to 6. So this is the most popular example of the smart world phenomenon. This phenomenon is presented in many of real network and in many of random graph models that we use nowadays. Okay, fine. Our first example is what our only example is a study in the World Wide Web. Here we want to in the World Wide Web, each node represents a web page, and its age are the hyperlinks to another web page. And the degree distribution of the many studies have found that the web page follow a power law decayment for several orders of magnitude. Many of the studies characterize two kind of coefficient gamma for this power law decay. When the web page is linked to another one, out of the web page, we have the gamma out. And when the web page is linked to a document in the web page, we have the gamma in. For different studies in this table, we have some values of that different studies have obtained. We can see how the value of gamma out change by the number of by the sample size, but the gamma in doesn't change doesn't change a lot. Actually, they report no change between this value. Another important study is the endemic was the endemic study that make the first one of the first clustering coefficient in web page. She defined or she assumed that the network are bidirectional. With this consideration, he concluded that the clustering coefficient was 0.107 H. Okay, in this table, we have some empirical results for the study of different networks. Here, Barabasi and Albert report those different studies where they report the cluster average of the node. They give the gamma value for output and input in some case, in all the case. Also give us the average path that is compared with the real network, the random network, and the prediction of this random network. And we can see how for some models and some network, we can have a good prediction, but for another one, we don't have a good prediction. For example, we can take the metabolic for the E. coli bacteria. In this study, we can see that the value of the real network and the prediction by a model, by a random model, looks similar. However, for another study, we can see that there is a big difference between the real path left and the prediction given by the random graph model. Okay. Well, the graphic theory can be applied in several areas, in sociology, biology, physics, etc. For example, in sociology, they study the animal behavior or the structure of the social structure of many countries or different social structure, like the army, on people working in an office, whatever. And with this tool that is the network theory, they can see how the network change between given different circumstances in the ambient. For example, I remember like some examples that they study the behavior of one species and how the behavior of the network change when they are in front of a predator. So there is a lot of application of the network theory. Okay, for us, many of work is to looking for a model that help us to study and predict some phenomena. For network or for real network, we are looking for a good model that help us to understand the dynamics of the network, how the network grows up, how the network change across the time, etc. The first model is the random graph given by Erdos and Remy, but it has a lot of limitation. Here we have the Watts-Strogatz model. This model is inspired by the social structure, where they represent the fact that real network have a small world, have the smart world phenomena. For example, I can be the friend of a friend, or for example, there is a high probability that I will connect it to another researcher that is linked with my thesis advisor. So this model tries to simulate how this phenomena appears in nature. For this model, we start with a ring lattice with n nodes, where each node is connected with their closest neighbor. We must to consider that the layers, that the number of node n must to be higher, bigger than one to have a connected network. Then randomly we rewrite each edge and in the lattice with a given probability p. Okay. Okay. Here, for example, we have an illustration of how the Watts-Strogatz model changed according to different values of p. If we have a p equal to 0, we will have a regular network. And if we increase the value of p to 1, we will have a random graph. Okay, for small values of p, the length of the graph scales linearly with the number, with the random side, with the graph size. For larger values of p, we can see that this scale like a logarithmic function, give a logarithmic function of the graph size. Obviously, the clustering coefficient will be depend by the value of p. We have an analytical expression given by the equation 5 that can describe the prediction for the clustering coefficient in this model. Okay, the degree distribution that is the average distance between nodes. Yes. Here, the L. Okay, I missed the bracket. Here the L will be the average distance of the node.
José Luis, Thomas have a question.
Yeah,
just asked, and it's answered. Yes, so it's the average distance between two nodes, right?
Yes.
Yes. Yeah. Fine.
Okay. Okay. Here. Okay. Also, the degree distribution has a dependence of the value of p. This value p will be introduced disorder in the network dynamic. With the average of the node degrees is still close to average to the value of key that will be the value key. For p equal to 0, we have a delta function that will be centered in the value key. So we are interested in how this change, how if we change the value p, many measurements will be changed. The most interesting measurement maybe is the spectral properties of this model, because as I told you, the spectral property density of the GCC matrix is related with the topology of the network. Okay, the spectral density has a dependence of the probability p. Okay, I'm going to show you in the next slide how the behavior of the spectral density changed, and I want to retook through this point. But here I want to tell you that if I have okay, for the spectral properties, we can see for the three momenta, the squidness, even if I change the value of p, the squidness of the spectral density will be still high. This high number represents that there is a lot of triangles in the network topology. Now, yes, let me show you how the spectral properties change if I change the values of p. For example, here in all the picture, we can see the semicircle prediction given by the semicircle distribution, and all these peaks are given by the spectral properties for the spectral density if I change the value of p. As we can see, if I'm going to increase the value of p, the spectral density looks more like the semicircle prediction. So changing this, we are going to have this form. Okay.
I just have a question.
Yes.
Okay. This the results you are showing in this slide is already published, or it's your part of your work?
No. It's already published. Many of the presentation is based on a previous review given by Barabasi and Albert
Albert.
researchers.
Okay. So this is in the Barabasi-Albert review.
Yes,
Okay. Thank you.
you're welcome. Okay, well, let's go to see another interesting model. This is one of the models that I like more because the previous model has a lot of limitation given by the nature of the network. For example, this is better to simulate how network change across the time and add new nodes. One of the things that I like of this model is how they simulate the behavior of the network and most precisely the internet network behavior. In real network, most of the case there are not. In most of the case, new nodes are added to the graph in different epoch on different time. Imagine, for example, 1 year shorter. Each time we are going to have new web page in internet, for example. And we can also see that different real network exhibit and prediction preferential attachment to the nodes. In the previous models, they have the same a new node has the same probability to connect to the oldest node, but the reality is not that way. So the Barabasi model has the intention to reproduce how this phenomenon appears in real network. Okay, here you have the algorithm. In time t equal to 0, we will start with a small number of nodes, and for every time step, we add new nodes. This node will have HE, and this A will be equal or less than the original number of nodes, and the connection of the new node to the oldest is given by this probability expression. In this equation, we can see that the probability that the new node connect with the node A is given by the degree of the node A divided by the sum over all the whole degree network node degree in the network. And before we make this connection, we need to update the values of the probability for the new for all the nodes, including the new ones. The new ones. Fine. Here is an example. For time 0, we have two nodes that they are connected. For time 1, we add another node and they connected with the previous node, and this is how the network is going to be increased. For example, in the time 4, here, we can see that the center node has a bigger degree than the other one. So there is a high probability that the new node in the next time step, the new node will be connected with this node. And if we increase or we simulate many time steps, we can see how this node is going to increase its degree value across the time. Okay. Okay. For the BI model, there is not an analytical prediction to the cluster coefficient. However, we know the cluster coefficient increase with the network size, and this increase or change according to the, if we increase the lifetime of the network. Also, this network have a power law tail for the the average path of the length increase as a logarithmic expression of the size of the network, and also we know that the node degree increase given by the expression the square root of 2 of n of the size of the network. Okay, as I told you, the clustering coefficient has no predicted. We don't have an analytical prediction for the Barabasi model. We know that the clustering followed approximately this expression, and we also observe a behavior of the smart. The clustering coefficient will show a very different. Sorry. Okay. The clustering, the network will show a power law that have this form, and this form will be very different for the other models, like the random models or the of the small world models that I showed you previously. Okay. Okay, the interesting thing here is the spectral properties of this model. We can see a bulk of the eigenvalue that looks like a triangle. The spectral property will be very different with the semicircle distribution, and the largest eigenvalue is separated from the bulk of the spectral distribution, and the value of this eigenvalue increase as n rises to the power of 1 over 4. Here we have the spectral distribution for the Barabasi model. Here we have the largest eigenvalue of this model, and okay, as your box say, all the models are wrong, but some models are useful. This is the case of the Barabasi model. Even that this represents how network in internet drop off, it has a lot of limitation. For example, in this model, we are adding just a new node each time, or the attachment is higher for the older network. But in real network, we can see that the adding of new node can be exponentially, or there could be new rules that there could be new rules for the attachment between two different networks. So I know this is not a course or something similar, but it's really interesting how this network works or simulate this network. So I'm going to propose you for the listener that are interested in the study of network to make this little exercise. We are going to create a program in any language that simulate the BI model. You can check the algorithm in the description of the video. There is a link to another web page where you can check. We are going to measure the degree distribution of the model at the final time for these different values, 1, 3, and 5. If anything's okay, your plot must to look similar to this one in a double log scale. And as I told you, this network have some limitation with the real network. So I propose you that make a chain in the algorithm and justify this chain. Why you think this chain can represent or can have a better approximation to real network, and plot the new results in this way. Okay. You can send me the result to my email with the subject via model simulation. I would like to discuss your results and your ideas. And that's all for me. Thank you very much. Special thank you for the seminar crew, to my friend Noemi and Thomas Gori for helping me in this presentation. And I want to invite you to our next talk, that is Quantum Measurement Theory by the Dr. Thomas Gori. And also for all the viewers in YouTube, please join the YouTube channel to check new talks and have new information about statistical and quantum physics given by the group in University of Guadalajara. So thank you so much.
Thank you, Jose Luis, for your presentation. So if we have some questions, then we will take the questions right now. So yeah, anybody just can ask questions now. And yeah, if there is any questions from the YouTube streaming, then Marco, please forward those questions, and Jose Luis can answer right now.
Like those make sense. The word with direct graph. How does the metrics change? For the first slide, okay. Word with direct graph. The short answer will be yes, because we have in some nature phenomena how these phenomena give us undirected graph behavior between the elements. So there is many sense that we work with directed graph in phenomena. For example, the neural network, they in some case in some neurons they have a directional connection between them. And how the metric change, I really know how that metrics will be change the behavior of the network. Obviously, wants to change the topology of the network. How the
I guess he is asking for the connection matrix, about the connection matrix.
We can show. Yes, if we have different way, if we connect this, now we can see how the dynamic of the graph will change, of the network will be changed, and we can study another property of the network. But I don't know how this can change precisely that dynamic in the network. Fernando Flore, Ananda asks, how the Stanley Milgram measurement of between America, how is computed? Yes. I don't know. I don't know how Stanley Milgram measured this distance between two American citizens, but maybe if we check in Wikipedia, we can see how he gave that conclusion. But it's one of the most popular phenomena for smart world. Is one of the most popular example of the smart world. Also, for example, in Facebook, there is some studies that say that this distance is lower than the Stanley Milgram proposed. But sorry, I don't know how it was computed. This is a new job for me. I will have a question about clustering coefficient. Okay.
But let me ask the question. Sorry.
Please.
Well, I also would like to thank you for the talk. I mean, it was really nice, and but I also want to motivate the students to ask more questions. So I know that now it's more public and more people are listening to us, but still we should not stop discussing things, right?
Yes.
So don't be afraid to ask questions.
Yes.
So my question would be, what is the meaning of the clustering? Well, I understand the meaning of the clustering coefficient, but what would be a large clustering coefficient and what would be a small clustering coefficient? So what would be large clustering? What would be little clustering?
Okay, that would be, for example, here in the original picture there is a cluster by the British cluster, that is the red one. This is a lower clustering coefficient, does not has a lower clustering coefficient, but between them they are still have a big connection, and the influence given in this node will be affect the other node. The clustering coefficient also is used to classify patterns in the similarity to the previous nodes, and that's all I think.
Well, I thought you see the numerical value now. I think the clustering coefficient is between 1 and 0, right?
Yes. Yes.
And then you mentioned that in some example you mentioned a clustering coefficient of 0.1. Would that be little clustering, and or would it be would it be strong clustering?
This must to measure a low clustering coefficient, a low value for the clustering coefficient. It will be like a also, I think it's similar like the correlation coefficient between two different variables. So I think that gives us a better idea of how the clustering coefficient, the values of the clustering coefficient and its interpretation.
I just have a question. It's more like a comment. So
Yeah.
for the clustering coefficient formula, what you have given, you are considering only the triangles as the clusters, right? So you are not considering hexagonals and all those kind of clusters, right?
Yes, only triangles.
Only triangle clusters. So this is the most simplified formula one can imagine.
Mm-hmm.
Yeah.
Yes, thank you, Soham. And also, Marco, give me a.
There is another question.
There's another question. Let me check. You the network of the page have grown over time. What about the connection between persons? Have a new measurement of mail? I didn't see new studies to measure the connection in person. I suppose that yes, there is a lower connection right nowadays that are given by Milgram, especially if we consider the fact of social network. In social network, we have a lower connection between different persons and not just follow one person in Twitter. I think a real connection between different people across the world. So I think this measurement is lower right now. but it's better to study the literature to check how this measure is nowadays.
Can I make a comment on this?